Okay, so we're going to look at first order differential equations with the use of this result, okay, where we have the acceleration equals to vdvdx. Okay, so let me explain a little bit about this and where this sort of result comes from. Okay, but ultimately it is going to help with questions that relate velocity with displacement. Okay, so we might need to find an expression for v in terms of its displacement, which we would normally use the letter x. Okay, so let's just sort of write down a few sort of definitions, notations that we're used to. So displacement, okay, well, we use the letter x, don't we? Okay, for displacement. Generally, these questions use the letter x. Okay. Well, velocity then is v, yeah, it's letter v we use, and of course we know velocity is just the rate of change of displacement, how displacement changes with respect to time. So velocity we know to be the rate of change of this, so we know velocity is dx by dt, yeah, so we know this. And then the third variable that we're interested in is, of course, acceleration. Okay, where we've got a equals to, well, remember, acceleration is the rate at which velocity changes. Okay, so that will be dv by dt. Okay, the rate of change of velocity. Okay, so we know these results and we've used them. So we used this result in the first sort of group of exercises on first order differential equations. We used a as dv dt. But it is useful to use this result sometimes, okay, because often they'll give us a question in regards to its displacement, x, okay, and we'll see this. So it's useful to set up a differential equation where the variables are v and x. So when we separate the variables, then it'll just, as I said, it'll involve v, it'll involve x. And because the question setup might have information regarding its displacement. So why is this true then? Quite simply, okay, why would this be true? And it's really easy to show. You don't need to sort of prove this in the exam. You don't need to show why this is true in the exam, but it's useful to know, right? Okay, because we're going to be using that result. So why is this true? Where does it come from? So if we go to what we know about acceleration, okay, acceleration is the rate of change of velocity. So dv by dt. Okay. Now what I can do now, I can apply the chain rule. Okay, right? So I can use the chain rule, and I can rewrite this as a equals to, well, when we use the chain rule, yeah, whatever's on the top here, obviously needs to stay on the top, so I'm going to put dv there. But because I'm using the chain rule, I'm not going to differentiate it with respect to t, I'm going to differentiate it with respect to x, okay, because of course I want to relate velocity with displacement here. So instead of writing dv dt, I'm going to write dv by dx. Okay, and with the chain rule, of course, you link it, so we're going to multiply. Question is, what do I multiply it with? Well, just go back to this and appreciate you need to have dt on the bottom. And of course, because I've got dx on the bottom there, I'm going to have dx on the top here. Okay. So when you think about it, as we've discussed with the chain rule before, with the link here, they linked by these dx's, and you could sort of think of these as cancelling out, because you've got dx on the bottom, dx on top, so they cancel each other out, and you're left with dv on the top and dt on the bottom, which is what acceleration is. So just using the chain rule there. And of course, what's good is then, well, dv by dx we leave as it is, but dx by dt, quite simply, is velocity, isn't it? Dx by dt is the rate of change of displacement, which is just velocity. So there's the result, okay, that we've got there. So of course we'll swap these around. So we put the v at the front and we get that, okay. But it is really useful to use that result, and we'll see now in the questions how we can apply it.